a small tech startup based in Calgary, and we specialize in services and building products. So for the services side, we do machine learning consulting, AI consulting, as well as software development. And for the second part, we build products that potentially can help solving some real problems in the real world. And so the topic of today, AI readiness, what exactly do we mean by that? We're going to touch on the foundation of any AI/ML system, which means data. We're going to be talking about data. So no flashy AI models today, sorry, but I think it's really important to talk about data, which is a cornerstone of any AI/ML system. So I'll just give you guys a little bit more context to the problem itself with the problem statement and some numbers. Then we're going to reflect on the problem with our personal experience. After that, we're going to go and talk about some case studies from the big tech companies in the industry, some of the biggest players, and how they struggle with data quality for AI systems. Then I'm going to hop into Jupyter Notebook to show you guys a little bit of demo. I'm going to try to build a simple ML pipeline showing how unprocessed and processed data can influence the results of the model. And we're going to wrap it up with the product we're actually building right now that's supposed to help with data quality/data governance problems called Norma. In this day and age, we keep hearing about all the AI success stories. Anthropic drops a new model every month. OpenAI drops a model every month as well. The majority of all the startups nowadays in San Francisco are AI-based, building some LLM wrappers. So we keep hearing about all the AI success, but nobody actually talking about the failures in the industry. And based on the Gartner's survey, 85% of all the AI projects in the corporate world fail. And you would think maybe it's because the model that was chosen was the wrong one to implement, or maybe AI in its current state is not ready for the industry, and it's sort of like a research field still, and we're waiting for AGI. But not really. According to McKinsey, 70% of those projects that actually fail because of data quality and integration issues. So it's a big problem. And to translate it to the dollar values, 5Trend reports 5% of global annual revenue is lost because of data quality for those AI systems. So I think we collectively think it's really important to talk about that topic today, earlier rather than later, and get down to the foundation. I'll quickly talk about one of my recent experiences with bad data at Synovus. We were in the process of moving from the legacy system to the new system for occupancy tracking. So the idea is pretty straightforward. We want to track where everybody is sitting, where everybody is moving from which office to which office, and so on. So this table shows a new system we just implemented, one of the tables from the API. And just a context, this table comes from a relational database from the vendor itself. So just by nature of the table, it should have some primary keys or foreign keys, and this table had none. So good luck joining multiple tables for a Power BI report or some other tasks. On top of that, look at the column types. All of the column types were strings. And this one is a funny one, I think. The column called number has a string data type. On top of that, the missing values as well, and repair cost, it has currency type plus the cost value in the same column, so it's not normalized at all. So a lot of work goes into just normalizing the table and making it more cleaner. And another problem with this table was that it's supposed to track the movements, as I said. So it should have, for example, on my personal experience, I recently moved from the office to a cubicle. And this table is supposed to show that I was in a cubicle, I was in an office, and I moved to a cubicle. So either a timestamp or a flag to show which record is the most current one. None. None of the columns were present. So let's say I'm getting laid off tomorrow. Good luck finding me and notifying me. Where do you go?
Very similar experience to Eugene. I did my internship at Suncor, and pretty much my entire 22-month internship was sitting and doing the exact same task every day. So I was on a occupational health and safety team, and this 3-month project, which took a little bit longer, 22 months, and still not done, I was supposed to build a dashboard in order to show the incidents, accidents, casualties, and the unfortunate fatalities that happened at Suncor sites all across Canada, mainly in Alberta. And so the data that this report was based on was software called eTracker. And this was a way for employees to write down, accidents or accident-prone items or anything like that, and then submit a form and input it into eTracker, which would, I would see on my site, and built a dashboard. And I would say that me and my team built one pretty good dashboard. However, the same problem that you'll see over and over again, the data behind it was flawed. You would think that this accident-prone data, this super important data to show who's getting injured on the site, where the money is going, employees and benefits and stuff like that that you have to pay out would be governed or at least cleaned, but it wasn't. It was a complete mess. This included anything like inconsistent company names, like you could spell Worley Parsons everywhere under the sun. I saw it. It was 2 million rows. It was crazy. A lot of misfiled incident reports, just missing fields, everything like that. So you can imagine as a director, you see this report and they wanted to start actually building some actionable insights to start saving people's lives and preventing injuries. And you can't do that. This is no longer a problem of just messy data and having kind of like a nightmare internship. But people's lives and people's well-being are at stake. And we'll see in some of the case studies additionally that this isn't just the case for Suncor or oil and gas, but it happens across all industries. So even with this dashboard, the amount of cleaning we did, and I mean, still as an intern, this team, we were putting every piece of technology we could to clean this data, right? Classification, NLP, machine learning algorithms, nothing fixed it. The dashboards were messy, directors couldn't read it, and yet every single day I saw more and more data come in about accidents, people falling. We had casualties that happened when I was there. So again, not just about messy data, but it goes on top of that, like what the data is actually affecting. So it's not just me, it's not just interns and just us complaining about data, but there are some real big business players that that exist in this world that have come to the same problem and have invested millions of dollars into products that just fizzle away. And the root cause is data. So the first two that we'll go over is IBM and a unnamed global food manufacturer. And these two had a very similar problem, invested millions into an AI development project that inevitably fizzled away, all from the root cause of bad data. And then the last one is actually a win. HCA Healthcare is one of the biggest healthcare providers in the US, and they actually spent a ton of time, a ton of resources into properly formatting their data, hence saving a ton of lives. And then you'll see how they're able to take this formatted data and progress their product in a way that they didn't even initially intend in their initial product scope. The first one is Watson. Have you guys heard of Watson from IBM? Most of you? Okay, perfect. So you know what I'm talking about. So in 2011, after beating the best players in Jeopardy, the obvious next step is to cure cancer. And so that's in 2013 when they released Watson for Oncology. And this big goal was to create personalized cancer treatments for a patient. Personalized cancer treatments for an individual patient because every single category or every single patient had a different story. So they made a huge investment of $4 billion and partnered with, Memorial Sloan Kettering. And, but after a few years, the project was just shut down. So why is this? They wanted to start getting into AI as soon as possible. I'm sure the same with all of you, you just want to start getting your hands dirty. But with a $4 billion investment, things have to work a little differently. They generated their data based on textbook perfect simulations. And doctors and data scientists created these perfect data and trained the AI on it. It immediately went to adoption without any testing. So they didn't test it in a couple hospitals or a couple patients or things like that. They immediately spread for worldwide adoption. And the data that you get from hospitals is extremely messy. It's doctors' handwriting, it's abbreviation, it's missing files. There's no standardized way, especially in the US with a different privatized healthcare systems, there's no standard way to express this data. And so the AI, knowing clean data its whole life, started ingesting dirty data. But this wasn't caught on immediately, and this is where the big problem happened. As a lot of you know, I'm sure when you ask Claude or Grok or ChatGPT any question, it'll always produce an answer, no matter what. It always wants to be right. And so that's exactly what the AI did. It wasn't a flawed model, but it was flawed data. And it started recommending treatments that were actually harmful or even fatal to patients. And so quickly, doctors caught on to, the second problem is that doctors would get a response from this AI. Feed patient X drug Y, but no idea why to do it. Their algorithm was a black box, and so there was no featured step to see, hey, this is the reason why you need to give this patient drug X or whatever it is. This is the process. It just told them. So quickly, this dropped off the face of doctors and treatment specialists all across the country. And just like that, their $4 billion investment crumbled. Again, they had the best AI engineers and scientists working on this product. The algorithms that they used and the papers that they provided were super, super helpful. They did a lot of good research, but it just wasn't adopted, and most of their investment failed because of the data that they ingested. Another super similar case study is this unnamed grocery store. Let's call them like grocery store, or a grocery food packing plant. And a pretty simple plan. They wanted to optimize their supply chain and their warehouse resources, right? So stock more cookies when it's Christmas season, keep it back in the summer. Pretty simple. But less than 10% of their $20 million budget went towards data cleaning. And a lot of this, and most of it was just for data ingestion. That's where like the budget mostly went, not even for cleaning or even looking at the data. And so seasonal spikes, high times, different economic factors were completely overlooked. All these outliers and dirty data wasn't categorized correctly. And hence, when they fed their AI model, it gave them completely wrong information again. Very similar story. It's not the AI's fault, but the data that was held underneath. Without proper investment and structure in their data, all of it came crashing down. The company ended up ordering way too much, so that also affected their investment. And same thing, within, I think, less than a year, their AI algorithm completely fell apart and their $20 million investment went wrong. And the data that they wanted to clean wasn't anything hard. This was things like standardizing SKUs or reading barcodes. Like this is stuff that like you do on an internship. Not super hard, stuff that like if you just spent a little bit of time, but upper management wanted to rush, they wanted to get their hands dirty right away. This case study I found the most important and actually the most interesting, so I will spend a little bit more time on this, but this is a part where clean data actually led to saving lives. So HCA is one of the largest healthcare organizations in the United States. They have over 185 hospitals, 2,000 care sites, and what they wanted to do was treat sepsis earlier. Sepsis is a very dangerous, I don't know what to call it, but like procedure or treatment that needs to happen, and you need to catch it at a very thin time frame. And the earlier you can start treatment, the better. So this is where they launched SPOT. It was sepsis protection and optimization of therapy. And their goal was to act faster and save lives. But they faced a ton of messy data in the start. Just like the first case study, hospitals don't have standardized rules for their treatments. And there's really only one treatment for sepsis, and it's a lactic acid test. However, even just something simple as a lactic acid test was named 700 different things, 708 different lab names. And so instead of trying to train on this data or figure out what it does, before they even touched an AI model, they began to standardize. They didn't just bring in a data scientist or the smartest data scientist, but they actually brought in nurses and doctors to teach these data scientists about the entire procedure so they would have a good contextual understanding of the actual data they were working on. This meant that they could standardize rows and understand the lab test names and try to get an idea of like where the data came from and what it needed to be. So even before touching the data, they got a good context. And so they did it. They did exactly what they wanted to do, and they standardized this with some Rosetta Stone. And this was the optimal foundation for starting SPOT, removing 20% of unnecessary fields and over 35,000 different, what do I have there? Patient records were removed, studied, and then now they have 31 million patient records that they're standardizing instantaneously. So once they created SPOT, it was able to flag sepsis 18 hours earlier. And again, the earlier treatment, the better. And it's estimated that they've saved over 8,000 lives. Again, this isn't any brand new cutting edge AI or machine learning algorithm that they did. It's the exact same resources that everyone had access to, but just with smarter data. Finally, the project went further than that. When the hurricanes hit the southern United States, they needed to evacuate thousands of people from a ton of hospitals. However, because they had standardized all the data, they were easily able to see which patients were on ventilators, which patients were bedridden, which ones were in urgent care, and rush them to the necessary hospital out of the evacuation zone and continue their treatment immediately. So this wasn't even in the scope of Spot. But just because they were able to clean the data and had that standardization, that perfect Rosetta Stone, their emergency flag for the hurricanes was flawless, and they were able to save lives that way. So I hope you can see now that it's not just us, it's not just interns, but it affects everyone, big companies, millions of dollars, and this is happening all over the place. Again, as Eugene mentioned, you hear a lot of successes, but what can we learn from the failures?
As I mentioned before at the very beginning, I'm going to show you guys two notebooks. And the whole reason is to show you the difference. So the one notebook is going to be very simple preprocessing of data, and the second notebook is going to be a little bit more robust. So the purpose of those two notebooks, we're going to compare. So we're going to fit the regression model at the end, and we're going to check RMC of the first notebook and the second one, and if we improved in accuracy. And before I'm going to do that, I'll try to show you guys the data set I'm working with here. So the data set is the housing market data set from one of the largest banks in Russia called Sberbank. And so the initial data set, it has a bunch of features, a bunch of columns, over 300 columns, I think. And the amount of rows is staggering as well. It's over 300,000 rows. So just for the purpose of the demo, and because I'm using this tiny CPU on my laptop, I dropped a bunch of rows. So I kept it at 25,000 rows, and I kept the first 20 features, I believe. So the target variable is going to be the price, called price doc. So the data set is transactions of the housing that was sold. So the price is the price that it was sold for. Timestamp is the date of the transaction, and you can see a couple of more features here and their descriptions, just basically characteristics of every single apartment that was sold. Without further ado, let's go back to VS Code, and I'm gonna load all of my imports here, and let's look at the shape of the data. So as I said, I kept it to 20 features. I have only 27,000 rows. And here's the breakdown of all the NAs in each of the columns. We can see that in the middle of the data set, we have quite a bit of NAs. So let's move forward. Some housekeeping. And we're going to drop timestamp and ID column. ID column just doesn't give us any information for the model. Timestamp, we're not going to be building forecasting here. So I'm not going to be treating this data set as a time series because I'm going to be fitting regression at the end. So timestamp, we'll just skip it for now. Let's see some basic information again. After we dropped it, 18 columns, the same amount of rows. Before I'm going to fit the regression model, let's check some of the assumptions. One of the biggest assumptions is normality and homoscedasticity, and the biggest factor for that is scaling the target variable correctly. Let's look at the distribution of the target variable, which is the price variable. We can see that it's highly right skewed, so we better scale it, or a model may not perform. We're going to use log for the right scale, for the right skewness, and we're going to apply log transformation on our target. And then the next step, we're going to split it into 80 and 20, 80% for training and 20% for testing. And we're going to build our baseline model with minimal preprocessing. So we're going to drop all the columns that include an A because regression model, it just can work with an A's. So we're going to drop an A's, and we're going to also drop any object/string columns that we have, since we need some numerical input for the model. And we're going to fit ridge regression model with alpha of 10, and we're going to use exactly the same model in the second notebook. So we're going to fit the model, and we're going to predict, get in the baseline prediction, and then we're going to calculate RMCE. And we're going to see residuals just to check the graphs if we met the normality assumption of the model. Here's the little report of RMCE we got. So we got 0.551 on the log scale, and We just need to remember that and compare it to the number we're going to get in the second notebook. And I'm going to save that just to load it to the second notebook and compare it with new results of the second model I'm going to fit. And before I'm going to do that, I'm going to actually transform it back to the dollars so we can compare apples to apples on the dollar scale. What's the percentage of decrease in the errors on the dollar scale? And just to show you guys that the model actually makes sense, we can see the residual plots on the right-hand side. What we're looking for is, are there any, is it completely random or are there any patterns in the plot? And as we can see, it's not perfect for both of them, but there are no any funnels or any strict patterns on the left-hand side. And on the right-hand side, what we're looking for is our residuals should follow exactly the straight line. It's not perfect, but it will do. It does make sense, not the perfect model, but it does make sense. So we'll just keep it there. The most important part from this notebook is the RMC we got. And I saved it right here in the text file. Again, no cross-validation, no fine-tuning, just simple model, just to compare apples to apples. So here's the second notebook. It's kind of hard with the mic. We'll load the data set, exactly the same data set. We see the same amount of NAs. Since we've already checked the distribution of the target variable, we're just going to go ahead and apply log transform. And then we would want to look at distributions of every single column to see if we really need to scale it, apply some scaling techniques, or they look good. And they don't look good at all. For example, the square footage variables, 3 at the top, they're not just right skewed. We can see that there are some pretty decent amount of anomalies on the right-hand side. The other ones, for example, the state one, there is some extreme values on the right-hand side, large numbers, when it's normal for the state to have some smaller numbers. So we'll address those. So for this square footage, we're gonna get rid of the anomalies and cap them at 1,000 square foot for kitchen and living space square footage. And I think it's the same for the full one. I kept it at 1,200. For the state, if it's less than 10, we'll just drop it. We don't really need that. Number of rooms, if we have more than 15 rooms in an apartment, sounds a little bit off, and graph shows that too. And the build year, for some reason, the dataset has a lot of build years that are below 1,200, which is 1,200. Very old, which is probably possible, but it's in Russia. Russia was in World War II, so the majority of Moscow was rebuilt. So we'll just drop them because I don't really want to spend too much time exploring why we have those. And we're just gonna do the sanity check and just drop duplicates. Let's go ahead. So after we got rid of some anomalies, we can see that we probably need to apply some scaling, at least something for our features, for numeric features. And I'm going to show you later. I've decided to just simply do standard scalar for now, which means mean of 0 and standard deviation of 1. We're going to go ahead and split the data before I'm going to do some further preprocessing. And I'm splitting the data before I'm going to show you the preprocessing I do, just to avoid data leakage. So nothing from the test set leaks into the train set. And then, so for the pre-processing and for fitting the model, I'm going to be using scikit-learn's pipeline API. And for that, I'll create classes for every single step I want my data to go through. The first one is imputer. So as we saw, there are a lot of NAs in the data, and we would probably want to impute those NAs with some sort of techniques. For this purpose, I've chosen KNN imputer, which is KNN is basically an unsupervised learning method by itself. And I'm choosing neighbors of 5, and distance, I'm going to be using Euclidean distance. So what it means is I'm separating my data set into different clusters with 5 data points in each cluster that looks similar in some nature. And then if the cluster has NAs, I'm going to be imputing those NAs with clusters mean. So I'll do that, and I'll do fit which is going to get the statistics from the trained data set. And I'm going to do transform, which is going to apply those statistics to the trained data set and test data set going further. The second one is feature engineering. Feature engineering is really important, enhancing your data with some additional data from the data you already have. The first one is living efficiency. I'm creating a ratio between living space square footage and full space square footage. And since I'm dividing by the full square footage, I'm just adding epsilon just to be sure we're not dividing by 0. We don't want that. This is the first one. The second one is average room size. I'm dividing the full square footage by the number of rooms to get the average room size. And then floor ratio, floor divided by the max floor. Then, as we saw, the square footage variables are highly right skewed. So I'm just decided to do a log transform on just one of them, just to see if it's going to help or not. And the last one, we do have some kilometers variables, which basically says how far is, for example, kindergarten or park, or what's the second one? The school one, how far is it from the apartment? So I'm just summarizing that in the feature called amenity score. And the further away it is, the lower the score, and vice versa. So those are the features I'm going to be adding to the data set on top of already what we have. And then, if you guys remember in the first notebook, we dropped all the non-numeric columns. Here, I'm going to encode those. We have a couple of object/string columns, and we're going to use one hot encoding for the low cardinality columns, and we're going to use frequency encoding for the high cardinality columns. So frequency encoding is basically how many times does the unique value repeats in the data set, which is going to assign that number instead of the string value to a record. I'm not sure if I was running those, so I'll just make sure they're declared. So those are the three steps. And I have the fourth one. So here's the pipeline. I'm building the pipeline. The first step is the imputer, the second step is feature engineering, and the third step is the encoder, and the last one is the standard scaler. Since we saw most of the features, I would say all of the features are not scaled properly, so we'll at least apply standard scaler for all of them. Then we're gonna declare the models pipeline. We're gonna preprocess the data, and then we're gonna fit the ridge regression model with the same alpha. If you remember the first notebook, alpha was 10 as well, exactly the same model. I'm not fine-tuning it here. Did I declare it? I think so. And let's actually fit the model and see, hopefully it's gonna work. Let's see if it actually improved any scores for us. So we are interested in RMSE, and it's lower on the log scale. On the log scale, it's not that big of a difference. It's still a pretty decent difference. But when we convert it back to dollars, which I'm going to do next, so I'm going to load the RMC in dollars from the first notebook. I'm going to convert basically the RMC score from the log scale back to dollars, and I'm going to compare dollars to dollars. What is our error from the first notebook without preprocessing, and what's the error in the second notebook with some preprocessing? Let's do that. The last time I ran it was 27% difference, and it stayed the same. So as we can see, the second notebook, I'm not doing anything crazy. It's still pretty basic preprocessing, but we already got 27% difference in the model performance in terms of the error score dropped 27%, which is in dollar amount, it's hundreds of thousands of dollars for the prediction. So in my opinion, this is pretty impressive. And again, this is like the data set. I found it, the first data set I found. I randomly selected rows, I randomly selected columns, just with some basic steps for the data preprocessing, knowing what you're doing. We already got 27%. I can imagine if, for example, I was a SME in the housing market, so I knew what features I could engineer better, what makes more sense, what doesn't make sense. It could bump the score even more with just basic preprocessing. Hopefully it shows you guys a little bit hands-on differences between pre-processing and not pre-processing data and how it influences the model at the end.
We talked about a bunch of things. We talked about our personal experience. We talked about the experience of others. And we even went through a live demo of using a notebook to clean data and see if it fits our ridge model better. And if you're still not confused, I have a question for you. How many of you know about the challenges that OpenAI is facing right now in training the next big model? One of the big challenges that they're facing is that they're trying to figure out where to get the next petabytes of data from. They trained GPT-4 on almost the entire internet. And now they're looking for more, where do they get the next data? It's not as simple as just generating more data from previous models. And as you can see, this this argument is basically that even our biggest and best models are still sensitive to the inputs that it receives. So I'm going to get a little bit more technical. I'm going to show you guys a little bit math, but don't worry, for those of you that their hearts skipped a beat when I showed the equation, there's only going to be one. And this is about actually what defines bad data. So any downstream task, whether that be reporting, model training, anything like that, the error comes from three main components: bias, variance, and noise. So there's bias, variance, and noise, and these are all the different ways that we have bad data. Now, those three things actually come from real-world problems. For example, bias can come from flawed sampling methods. Or our variance, if it's too high, it could be because we just don't have enough data. And then noise just could be limitations in our measurement devices. So whenever we do something like reporting and training a machine learning model, we're actually taking data from the real world, which there's some aberrations that come with that, and we want to do something with that. Cool. So my argument here is humans alone cannot do all of this by themselves. And this is where we recruit the help of AI. And here are the reasons why humans can't keep up. There's a lot of data that these days we gather. If you work at a large company, you know exactly what I'm talking about. New tables come hourly. Schemas change. And there's so much volume that if you have a petabyte of data, your results will just time out. And like Eugene mentioned, he wasn't even able to fit the model on the entire data set on his tiny laptop CPU. And then there's variety. So every day the data looks different. The pipelines that you create today may not work tomorrow. And then there's drift. The data that we work with today, over time, can get worse and worse, and there's just no way to kind of figure it out. So here's where AI comes in. AI can actually look at a lot more data than we can in the same amount of time. It can stay consistent, and it can bring the insights from machine learning and data science research and keep up to date with the best practices as well. Okay, I'm going to show you guys a little demo, and here are the different things that we're going to go over. I'll show you our summary and catalog features, and our actions, SQL generation, and change tracking. Okay, I don't know whose bright idea it was to have 2 live demos in one presentation, but we'll see how this goes. So this is probably an interface that is kind of familiar to a lot of you. You have a table, and you can do what you would expect you can do, like manipulate the cells. You can select different tables, things like that. But what I want to show you guys is the different features that we've built for data scientists like yourself. So number one, we have a summary feature. And essentially what this does is help you understand what data is it, what are you actually looking at? So normally, when you have a data set, you have millions of rows, thousands of columns, are those normalized? And then all the statistics that you would pull up anyways using pandas or whatever. And then the next thing, which a lot of people are starting to adopt, is the catalog. This is kind of like, what columns are you working with? What are the descriptions, data types, and things like that? We're developing a cool feature that allows AI to actually fill those things out for you, but we'll leave that to another time for now. All right, let's look at something real. So I'm going to pick a much larger data set. So this is the same data set that Eugene was working with in his notebook. And I'm going to show you guys how much easier it is to use something like this, or to use AI, actually. All right, so one of the things Eugene did and spent some time on was imputing null values. So as you can see, like these different, you see all these like empty cells? Those are nulls. And nulls make it hard for us to train models. And the reason for that is because now, if I were to use this feature, either I could just drop it, or I could like give it a value like 0. 0 would introduce bias. And if I were to drop it, now we're reducing our data set size. So one of the cool tricks we do as data scientists is to impute those values. And this is, like the basic idea is to look at all the other rows and see if we can fill in the holes. All right. So Eugene, how long did it take you to do an imputation? A few hours? Okay, well, let's see how long it takes with us. Like, let's take life. Let's do this one, for example. Hit apply. In the background, this triggers a Python kernel, and we use like the efficiencies of Python to actually produce the values. And the AI actually even like figures out what methods to use. So when we're doing an imputation, there's a bunch of different ways to do this. You can use mode, median, linear, like regressions. Here it chose to use KNN, and it also figured out which columns to use for that KNN imputation. And so you can see, like, it just automatically kind of like filled in those holes, which probably is better for my downstream task. Okay, now let's look at something else. So this is kind of like our actions feature. The AI actually figured out, okay, you have a bunch of nulls, you probably need to impute them. And so it's come up with those different actions for you. And then you can also see another one of our actions is to remove outliers. So I guess it detected a few outliers in our data set, which also Eugene mentioned with all the graphs that he showed. So actually, this is a collection of a bunch of different machine learning models. And you can use any like LLM you want in the background. For us right now, for this demo, we're using Claude Sonnet 3.7 reasoning. Actually, for this, like what you just saw, we're not making an API call. We use different heuristics to figure out if we should use KNN and stuff like that. And then we just apply them. None of this has ever went to OpenAI yet. Actually, that's a great segue to the next feature, which is more like a chat interface, which a lot of you probably have also seen. And the idea here is you should be able to chat and ask it to do things with your data. So in this, actually, we're going to use Claude to do a tool call. So like my question will go all the way to Anthropic, and then we'll get a result. So one of the neat things about this is we can straight up just use SQL like we would normally. But I am a little bit rusty, so let's say I'm not sure how, I don't really remember how to do this with just pure SQL. Let's ask it to find rows. It decided this was not an SQL statement, and then it went ahead and pushed this to Anthropic. And Anthropic's Claude model figured out, okay, this is the SQL statement you should execute to actually get the answer that you're looking for. So all of these rows have floors between 3 and 8. Okay, So that's cool. We've all kind of seen text to SQL, old news. Let's figure out a little bit more of a difficult question. What if I had no idea how to answer a question like this? First of all, there is no column called price. And really, there's no column called number of rooms or area. So the LM has to do a few things to actually answer this question. First of all, it has to figure out the SQL to execute. But more than that, it has to figure out what exactly are you talking about. So it uses its understanding of the data to create this SQL statement, and then it's come back with the correlation. So it looks like the area is a little bit more important to the price than the number of rooms. And like that's part of like what we're trying to solve here. We're trying to figure out, okay, how do we look at this data objectively? And when you have a tool, something like this, you're able to look at it with a different lens than if you were to look at it with your own eyes. One of the problems with being a data scientist is you have to like think about like large groups of data, and you can only check like certain pieces of it. So you have to kind of like introduce what you understand about the data, not actually look at it objectively. So if you mess up though, and you ask the AI to do something that you just did not want it to do, the way we've built it allows us to track every change that you make. So if you can see here, this is kind of all our revisions. So I've kind of done like 2,000 kind of things on this data set over time. And basically what this allows us to do is like say, okay, oops, AI made a mistake. It deleted my data table. Sam knows about that happening a lot. I mean, probably all of us know about that. And you can just, if you would like, you could just go to a different version. Just hit version 2005, like whatever, and you can just straight up just push it back to that. So that's a feature that we kind of like got inspired from like Snowflake and Databricks and those guys. Basically, all of that we did, what Eugene did in maybe 3 to 5 hours, we did before the coffee even cooled. So the amount of like time savings that you get as a data scientist, the amount of cognitive load, like how much you can reduce it, it's like huge. We did the nulls thing that Eugene did. We did the same reduction in error. And so we think that we can improve productivity 3 to 5 times and improve reliability overall. Okay, so this is kind of like what we're looking to kind of target next. We think that sending your data is probably not ideal for situations where your data is private and stuff. So we want to anonymize it before we send it to Anthropic. We want to generate visuals for you, so you can have charts and graphs, and maybe you want to export that to PowerPoint or Power BI. We also think that some of your data sets, you could supplement it with external information. So we could go and find those data sets for you. One really cool thing that we're thinking of is task-aware cleaning. So if you tell it, hey, I want to train a machine learning model to predict the price of a house based on the number of rooms or the square footage or whatever, how the data should be manipulated is a lot different than if I wanted to report on this. And then finally, we want to be able to capture if your data is drifting over time.